Talked about organic molecules acting as acids and bases, whether we're using the Bronsted or Lewis definition. We've looked at those mechanisms of those reactions and used arrows to show electrons moving around, forming bonds and breaking bonds to show how those acid-base reactions work. And we've quantified how well things act as acids, bases, whether they're strong acids or weak acids. We've used pH values, we've used Ka and pKa values to quantify acidity. What we're going to talk about today is really looking at the structure of molecules and being able to determine which ones would be better acids or worse acids. These questions come up on MCAT tests or the ACS exam when you're given a set of molecules and asked to rank them in terms of their acidity from least acidic to most acidic. And so how can you do that? How can you look at molecules and determine whether they're going to be good acids or not relative to other molecules? Well, we're going to look at a certain set of characteristics that we can remember through this mnemonic called cardios. And we look at each of these 5 characteristics when we're considering a molecule to determine whether it's a good acid or not. We'll look at the charge of the molecule, whether it's positive, negative, or neutral, what type of atoms are in the molecule, how big they are and whether they're electronegative, whether there are resonance structures available to the conjugate base, whether there are atoms that promote a dipole induction in that conjugate base, what type of orbitals are present in a conjugate base, and whether the conjugate base can be effectively solvated and stabilized or not by the solvent. So let's look at these different characteristics one by one. We'll start with the charge, and really, this is a pretty simple concept. If you have a positively charged molecule, it's probably going to be a better acid than one that is neutral or one that is negative. In order for a molecule to be an acid, it's going to have to lose a positive charge, and that's easier done if it has extra positive charge on the molecule in the first place. Imagine if you're a negatively charged molecule and you are asked to lose another positive charge to become even more negative. That's less favorable than if you have excess positive charge that is going to be lost when you react as an acid. So let's see an example of that. Here are some molecules: our hydroxide ion, water, and our hydronium ion, H3O+. The positively charged molecule, it has a much easier time losing a positively charged proton, and that's reflected in the pKa values. If we look, hydronium has a very low pKa value of negative 1.7. Water, which is a weak acid, has a relatively high pKa value of 15.7. And our hydroxide ion, which is not an acid at all, we can't even measure it as an acid, doesn't even have a register. We can't even register that reaction happening, so it doesn't even have a pKa value. Remember, since Ka values are the products of reactants for a molecule acting as an acid, for example, hydronium is going to act as an acid to form H+, and water as its conjugate base. That reaction can be described by this equilibrium constant Ka, and we take the negative log of that, negative 1.7. The lower the pKa value, the better the acid when you're comparing different molecules. Although we can't use 7 as a neutral point, we can say that the lower the pKa, the more acidic a molecule is. And so best acid, second, third. Here's another example. We have 3 molecules here. We've got something missing on one of them. Here's our NH2. This should really have a negative charge there. So it's much easier for NH4+ to lose a proton to form NH3 as its conjugate base. It's more difficult for NH3 to lose another proton to form an NH2 conjugate base, and it's extremely difficult for this negatively charged molecule to lose another positive charge to become 2- as a conjugate base. So if we were to rank these in terms of relative acidity, say most acidic, next least acidic. Okay, now let's look at the next criteria in our cardios mnemonic, and that's what type of atoms are present. Now, if we think about the atoms in a molecule, we're going to consider two characteristics of those atoms: whether the atoms are electronegative and really how big they are. And sometimes these two considerations work in opposition to each other. When we think of a conjugate base, that conjugate base is more negative than the acid. Either it is negative or it's become neutral. We can imagine that electronegative atoms could stabilize that negative charge. If we have things like halides, chlorine, bromine, iodine, fluorine, they like negative charge and therefore can draw that negative charge toward them, and it would be a better acid. Okay? Now, the other consideration is whether you have a big atom or not. If you have a larger atom, then that negative charge that's present in your conjugate base is more diffuse. It's spread around a bigger area on that big atom, and that is more stable than if you have a little pinpoint of charge on an itty-bitty little atom. So let's look at some examples of this and see if we can make some judgments here. Here we have, it looks like very different molecules: HF, water, ammonia, and methane. All of these have protons that potentially could be donated and could be acids, but those protons are hooked onto different atoms: fluorine, oxygens, nitrogens, or carbons. And here we see a real electronegativity trend. We have a very electronegative fluorine, less electronegative oxygen than nitrogen and carbon. And if we look at the periodic table, they just sort of run across carbon, nitrogen, oxygen, fluorine on a row. And so here we see a real electronegativity trend. F minus as a conjugate base is going to be much more stable than CH3 minus, because that electronegative fluorine is much happier being negatively charged. When the conjugate base is more stable, that means that the acid is a better acid, and we can see that reflected in a low pKa value. Now, what about consideration number 2 here? Well, it seems like the electronegativity wins out. Which is bigger, carbon or fluorine? Well, if you remember intro chem, carbon is bigger, but the difference isn't enough to overwhelm the electronegativity differences between these atoms. Now, here's an example where we have a bunch of electronegative atoms attached to protons, and really the difference is what's the size of that electronegative atom. Here we can see that number 2 dominates. We've got a small itty-bitty little fluorine molecule or atom, larger chlorine, larger bromine, larger iodine. Here we're going down in the column on the periodic table, and as we go down, we see that the acidity of the molecule increases greatly. Really, the explanation is that I minus, right, the conjugate base of HI, would have that negative charge dispersed among a bigger area, and that's more stable than a tiny pinpoint little F minus. Looking at this, F minus is such a small, unstable conjugate base that HF isn't characterized as a strong acid. It's really a weak acid, while HCl, HBr, and HI are all strong acids. So there are 2 considerations when we think about what atom our proton is attached to in the molecule: really how electronegative it is and how big it is. And we can think about it as going across the periodic table and going down the periodic table, sometimes countering each other. Here's an example. Which of these is a better acid, water or H2S? Well, if we look at the periodic table, they're both in the same column on the periodic table, and sulfur is just a bigger atom, and it turns out this is going to be much more acidic than water. Okay, now let's move on to our next characteristic. Let's see if I can get rid of these things, and that is resonance. Now, we've talked about this a little bit with regards to acidity, in that resonance can help stabilize molecules. Having more resonance structures is better for particular molecules. And let's think about that with regards to some common organic molecules. Here's one. Let's see if I can get this to work for me.